So we're here to talk about rolling and how to do conservation of energy analysis when you have an object that is rolling. And of course, the notes from fall 2019 and the video from fall 2019 were posted on Blackboard. So you should use those as the primary lesson. But I'm going to do an example here today. Rolling involves rotation, which has rotation is described by a variable called omega, which is the rotational speed, which is equal to v over r. So if you have some rollable object, a cylinder, a disc, or a ball, or something like that, that is rolling along with a speed of v, then it's going to have an omega of equal to v over r. And this omega is in radians per second. So the omega is describing how many radians per second of rotation our object has. The next important thing we need is the total kinetic energy, which is K translational plus K rotational. And we know what the translational kinetic energy is. That is 1/2 mv squared. But we need something to account for the fact that when something is rotating in place, it has additional kinetic energy beyond the regular 1/2 mv squared of the entire object. So if you have this object that is spinning and moving, then we have to add 1/2 I omega squared. And this I value is moment of inertia. And it describes how difficult it is to make something spin. Just like mass describes how difficult it is to make something move, moment of inertia describes how difficult it is to make something spin. And for all rollable objects, I is proportional to mr squared. And I like to call that proportionality constant fraction a over b because it always looks like a simple fraction. So as an example, solid ball I is equal to, the solid one is 2/5 mr squared. So in the case of a solid ball, that fraction happens to have a value of 2/5. Well, in the notes in the lesson, I described how this is actually equal to 1/2 mv squared plus a over b times 1/2 mv squared. So the amount of rotational kinetic energy is proportional to the regular translational kinetic energy, and the proportionality factor is the same a over b fraction that pops up in the moment of inertia of the object. So what I want to do is look at kind of the same example that is in your homework, but do it for two different types of objects. The first type, we're going to have a bead that slides along the wire without friction. And the second time is we're going to try it for a solid bead that rolls instead of just sliding. So let's see how the energy analysis looks different. First, let's look at the original case, the one that's actually in the homework. We start out with some energy MGH up here. And when we fall down to here and then come up to the top at point A, then we're going to go from a height of h to a height of 2r, because the bottom, the y equals 0 point, is implied to be the bottom when I call this initial height y equals h. So the y equals 0 must be h below that, which is down here. So this is y final equals 2r, or you could even call it y at point A is equal to 2r. And then that, according to the drawing, that height at point A is lower than the height h. So we're going to have some excess energy, because this mg2r is going to be less than the mgh. And where's that excess energy go? Into kinetic energy. So this allows us to calculate the speed v sub a of the bead at that point. Now let's try it for the solid ball, or the solid bead that rolls without slipping. So this is going to be I'm going to do the rotational specific example stuff in different color. I equals 2/5 mr squared. So when we do our energy balance, it's going to be initial plus work equals final. And our initial energy is just mgh. And we don't have any work, so that ends the left side of the equation, just like before. And we'll still have this 1/2 mv sub a squared. But now we'll also have a 2/5 of 1/2 mv sub a squared. And then at the end, we'll have plus mg times 2r. So you see that what this extra idea of rotation does is it puts an extra term in the equation. And that means that whatever energy is left over when you go from height h to height 2r, that energy difference is not focused into the regular translational energy, 1/2 mv sub a squared. It has to get shared between the regular translational 1/2 mva squared and the rotational energy, which are linked together with each other because our object is rotating. So let's set this up. Let's do m equals 1 kilogram to make it easy, and we'll do h equals 2.0 meters, and we'll do r equals 0.2 meters. Yeah, that'll work just fine. So in this version over here on the left, we're going to want to try to solve for VA. So let's just take these two numerical terms and gather them together on the left side. mgh minus mg2r. And this one is just 1 times 9.8 times 2 minus 1 times 9.8 times 0.4 equals 1/2 mv sub a squared. So now the first one, 9.8 times 2, is 19.6 joules was our starting energy. 9.8 times 0.4. My calculator crashed. 9.8 times 0.4 is 3.92 joules. That is 1/2 mv sub a squared. So 19.6 minus 3.92 is 15.68. That's how much kinetic energy we have, and that's equal to 1/2 mv sub a squared. And now we can solve for v sub a, and 2 times 15.68 over 1, because our mass was 1, is equal to v sub a. So we get square root of 2 times 15.68, close parentheses, equals 5.6 meters per second. So that's kind of how to do part of your homework. And now I want to do the same thing for the case where instead of sliding without friction along this wire, it's on a track and it's rolling without slipping. So now we're going to have our mgh minus mg times 2r equals 1/2 mv sub a squared plus 2/5 of 1/2 mv sub a squared. And this side again is going to come out to 15.68, just like before. But now we have to figure out how much of that energy is in the translational energy and how much is in the rotational energy. So if we combine these things together, then this is going to be 5/5 of 1/2 mva squared, and this one's going to be 2/5 of it. So that's a total of 7/5 of 1/2 mv sub a squared. So now to solve, we can just take 15.68 times 5/7 and get 11.2. So 5/7 of 15.68 equals 11.2, and that is our 1/2 mv sub a squared. So now our v sub a is equal to the square root of 2 times 11.2 over 1. And that comes out to 4.73 meters per second. So what we find is that the rolling object ends up going a little slower than the sliding object. Now in the lesson and in the video specifically of the lesson, I think there's a race between different objects. And as it turns out, the more energy you siphon off and use up as rotational energy, the less energy that is left over to be regular translational energy, and the slower your object will end up rolling. And this velocity calculation bears that out and shows how that's true.